Okay, as you're finishing cutting, a couple announcements here. First of all, you should, there's a recycle right back here, Modesta. You might notice that on your Desmos Match My Parabola, you might not have got the full 5 out of 5. I actually graded that on accuracy. So if you didn't get the right quadratic to go through the dots, the computer gave you an X instead of a check mark. Okay, so a lot of you got like 3.7 or 4.1 or something like that. If you want to relook at that and let's say you got a 3.7 and you really want a 5.0, then relook at that one and see which ones you didn't do correctly. One tip on that I noticed, if you, for example, I want to say one of them involved like a coefficient of 1/3. Well, if you use 0.33, 0.33 is a decimal approximation of 1/3. So to the naked eye, it's going to look like it goes through the dots and it looks good, but the computer is going to say, you didn't get the right one. They want you to use 1/3, not 0.33. That's just one example of trying to get it accurate so that you are adjusting your parabola accordingly. So you might want to take a look at the grade that you got on that and determine if you want to look at it again. You should have turned in 2 things on Friday. One was the used car activity and one was the quadratic worksheet with the 5 applications. If you either have a blank or a 0 for one of those, that means Oren did not see it when he was going through collecting them Friday after class. So you can still do it. You can still turn it in. But you got to let Oren know. If you have a piece of paper to hand him, you should hand it to him. And if you have something that's in your shared folder, you just need to let Oren know. If you already emailed me about it, I already talked to Oren about it. So take a look at that. Okay. You had a video quiz that was due today, and I saw most of you did it. If you didn't do your video quiz today, today's going to be tough. If you didn't watch that video or you didn't do that quiz, you're going to be lost today. I'm going to say that's your fault, not my fault. Okay? So we're going to do 2 activities today. One is involving the paper that you have, and the other is a Desmos activity that we probably won't finish in class, but that'll be your assignment for next time. We'll get started in class. Here's what I'd like you to do. Go to Blackboard. Go to, I'm on the wrong class here. Nope, I'm on the right one. Go to Course Docs and Links. And go all the way down to 5.2 and 3, polynomial functions, and 5.2 and 3 under the video quiz. Polynomial functions and their graphs, where it says that constructing polynomials, Desmos will do that later. So don't go there yet. I want to work on this 5.3 box building. Okay? That's what we're going to do. So the first document there is an Excel spreadsheet. Go ahead and open that up. And this is just going to be for you to punch your data into. So you can just have yours open on your own screen here. Should look just like this. And I'll zoom mine so it's a little bit bigger. With the yellow boxes in it. Everybody got that pulled up? So be ready to type some stuff into the yellow boxes. The next one is just the grid paper that I already printed out for you, so you can ignore that. So here's what we're going to do. We're going to take this grid paper, and I want you to imagine cutting the corners out. Don't cut yours yet. Cutting the corners out, like a little square corner out of each corner, and then you fold the flap, fold the flap, fold the flap, and fold the flap, and it makes a box with an open top. Can you visualize that? So I gave you a couple pictures to look at. Let's say, and you don't have to open these on Blackboard unless you want to. You can just look at the screen. Let's say I took your piece of paper and you decided to cut out, these are centimeters, by the way. The grid's in centimeters. So let's say you decided to cut out a notch out of the corner 1 centimeter by 1 centimeter. That means you would cut out just that corner box, 1 box, right? And you did that in all 4 corners. If you did that, and then you folded up the box, can you guys see how I folded up the edges? I now have an open top box. You guys agree? So now let's look at our spreadsheet. Your paper that you're holding is 25 centimeters the long way, 19 centimeters the short way. If you don't trust me, you can count the boxes. There's 19 going that way, 25 going that way. So this very first line says, if I would have done what I just did, if I would have cut out one corner, do you guys agree that the height of the box is now 1 centimeter? So let's fill in the first one together. If I cut out the square centimeter cutout, if I cut out 1 square centimeter from the corner, the height of the box is 1. I already filled it in for you. How long would the box be?
24.
Not 24. 23. Why?
Good catch.
Because we cut 1 off from the left and 1 off from the right. It was 25, minus 1, minus 1. Now we're down to 23. Do you guys agree? How about the width? 17. Exactly. Okay, how do you calculate the volume of a box? Length times width times height. So pull out your calculator, or if you're savvy, just use Excel. How can I do it on Excel? Equals, what am I taking? What times what times what?
B.
Yeah, if you want to use cell references, you definitely could. It would be B4 and B7. If I just wanted to use numbers, it would be 1 times 23 times 17. Do you guys agree? 1 times 23 times 17. So the volume of that box would be 391 cubic centimeters. This box right here. 391 cubic centimeters. Everybody cool with that? Okay, now I want you to imagine that instead of cutting out a 1 by 1 box out of the corner, what happens if I cut out a 2 by 2 out of the corner, each corner? My height is now 2. My box would look like this. See how it's taller? And then you got to figure out the length and the width. And then I have a couple more pictures. What happens if I cut out 3 by 3? If I cut out 3 by 3, my box would look like this. Each time I'm doing this, the box is getting a little bit taller. Do you guys agree? But it's also getting shorter in the width and shorter in the length. Okay? What I'd like you to do is see if you can fill out all of the bright yellow boxes. All of the bright yellow boxes. And if you do that correctly, and if you can do standard 7, look for and make use of structure, and standard 8, look for and express regularity in repeated reasoning. When you get to the dark orange one at the bottom, I want you to, instead of using numbers, you're going to use X. Instead of cutting out, 2 squared or 3 squared or 4 squared, what happens if you cut out X by X? Then what would the length be? What would the width be? And how would you calculate the volume? So ultimately what I'm looking for is, can you fill in the formulas for the dark orange at the bottom? I'll give you a few minutes to work on it. Go. Hopefully you see a pattern developing and you can fill this spreadsheet out really fast. Now, when you have your bottom dark orange row filled in, flag me down. I'd like to look at it. You got yours down? Just sure what you're asking here. So now I want it in terms of X. So I'm not giving you a specific number. I'm saying what happens if I cut out a corner that is x by x, where x is any number.
It should be b times c times a.
But what are b and c and a?
Oh.
You're correct.
Yeah.
Yeah, well, it would be. But what would go in that box right there underneath?
Length.
But what's the length going to be in terms of x? It's the formula that you use to calculate all the ones above. But now I want you to express it in terms of x. So a lot of you are figuring out that going down, we went from 25 to 23 to 21 to 19 to 17 to whatever. So what's the formula that would go in the dark orange box such that whenever I punch any of these in, it would give me that number? Don't overthink it. It's super easy. How did we get the 23? We started with 25 and we subtracted 2. Actually, we subtracted 2 times 1.
L minus 2x.
Right, except what would this is the L. So we're just starting out with 25 and we're subtracting 2x, right? Isn't that all we're doing in that first column? Or I'm sorry, in the second column, column B? We're starting out with 25. If we subtract 2x, it'd be 2 times 1. Here, if I subtract 2 of these, it'd be 2 times 2. That's how I got 21. 25 minus 2 times 3 is 19 and so forth. So what I'm saying is, this would be 25 minus 2x. Do you guys agree? Where x can be any number I want it to be. X doesn't even have to be a whole number. X could be 7.942. I could do that, right? So what would column C look like? You guys have already identified the pattern. 19, 17, 15, right? 13, 11, and so forth. What would my formula be at the bottom of that column?
19 minus 2x.
19 minus 2x. Exactly. So now the very last column. How would I calculate the volume in terms of formula?
X times 25 minus 2x times 19 minus 2x.
Very good. I'm taking all 3 columns, column A, B, and C times each other, right? So it'd be x times 25 minus 2x times 19 minus 2x. See how that last column works out? That formula that I put down in D13, that formula would calculate the volume of any size box that I chose to cut out of the corner. Right? You guys cool with that? So here's what I want you to do. Now I'm going to actually let you think about cutting out your paper. You should have calculated the volumes going down. Which one had the largest volume? Was it when the height was what? 4? Do you guys agree? When it was 4, what was my volume? 748. That's the largest volume on your sheet?
Yes.
So I'm telling you right now that if you want to maximize the volume of your box, the answer is not 4. Because all we did here is we did whole numbers. Correct? I want you to figure out what value should I cut out of my corner such that it'll make the largest volume box possible. And I'm telling you, the answer is not a whole number. Okay? I want you to round it to, you're solving for x. X equals something, round to 2 decimal places, or to the 100th. Round to the nearest 100th. And I'll give you another clue. You're going to need that formula down in cell D13. If I were you, I'd try to graph it. See what you come up with. Try to graph that formula at the very bottom of your spreadsheet and see if you can find the x value that would give us the largest box possible. Do you still have yours?
Thank you.
When you think you have something, let me know. I'd like to see it. What you've made now on your spreadsheet, this very last formula that you have, that is a function. It's a volume function. So I could call it V of x if I wanted to, or f of x, whatever I wanted to call it, where x represents the height of the box, which is the amount that we cut out of each corner. That's the height. And f of x or v of x or whatever I call it would represent the total volume of the box that I made. And we want the largest. Okay. Anybody got anything? Has anybody tried graphing it? A couple of you guys got it? What'd you get?
Is that right? 4.27?
I can't read that. Which one is it? Which dot is that?
E 4.27?
No.
No.
Well, first of all, that's the height. Let me look. Oh, you're missing a parentheses. See beside your 2x? You're missing a parentheses.
When I put it in there, it doesn't let me.
There.
Do I need to take this one out?
Yeah, you have one too many. Hit enter now. There, changes everything.
Yep. What do you got? Very nice. Very nice. Anybody else? So you graphed it, right? So your graph looks good. What point on the graph are you interested in?
Mine's black.
It might look like it's infinity, but use common sense. Can we make a box that has infinite? No, there's a certain domain that we can only handle here. We can't go beyond 25 by 19, right? So some of you need to scrunch your axis better so that you can see it. Yeah, when you graph it, it's going to look terrible. Use your perfect, just like that. Use your little crosshairs tool to scrunch your y-axis down so you can see your curve. So you can see it. You could move your x-axis over and make it wider, slide it over. There, that's a better picture now, right? What point on the graph are you interested in? Maybe you got to ask yourself, what's the label on your y-axis first of all? If we're labeling our axes, we already said x was going to be the what? The height. What's y going to be? Volume. What are we trying to accomplish here? Make the box with the largest volume. Therefore, what point on your graph are you interested in? Maybe the highest point? I mean, come on, guys. This isn't rocket science. The highest point on the graph would be the highest volume. However, some of you already figured out that that graph is going on and on forever and ever and ever. So then look at your x values and ask yourself, is that even feasible? Could I even make a box with the values that are going on forever and ever? Think about what the appropriate domain of your graph would be. Very nice. So you got the graph. What point are you interested in? Right there. What is that point? See if you can figure it out. Remember we have that button on our computer called Extremum? Yeah, very good. You're missing oh, no, maybe not. Let me see your, scroll that over so I can see your algebra window. Okay, yep. Now you just got to get your graph to look better. Get your axes better. Here's what your graph should look like. Now, some of your guys' graphs look like this. Some of yours look like this because when you punch it in, it doesn't give you a very nice picture. You got to scrunch it way down. And then I could move this over a little bit if I wanted to, whatever. Like that's a decent graph. I can visualize that graph. So notice that our formula, we took this from our Excel spreadsheet, right? And we punch it in and it gives us this this graph. Let's look way off to the right. Like over here, it looks like it's going up and up and up and up forever. So for example, let's say x was equal to 17. That's a pretty high volume, right? I'll just pick x equals 17. Can I make x equal 17? Can I make x equal 17? Can I make a box that has a height of 17? So that would require me to cut 17 out this way and 17 out this way. What's going to happen? Can I make, remember, I've got to do it to all four corners. Go ahead, Hannah. There's not enough paper. Isn't it only 19 total? Is there any way to cut 17 out this way and 17 out this way? That adds up to 34, and I only have 19. Do you see how these points are irrelevant? We don't have enough paper for that. So even though the graph is showing a domain that goes on forever and ever, our domain only has a certain amount of paper that we can use. What is the maximum height that I could make? 9.5. And what happens if I cut 9.5 out this way and 9.5 out this way? How much would I have left over for my width? Nothing. I would just be folding it in half, wouldn't I? And if I fold it in half and I have no width going this way, what kind of volume am I going to get? 0. So look at the graph. What's happening at x equals 9.5? Make it a little bigger here. If I try to make x equal to 9.5, it's right here. What's the volume if x equals 9.5? 0. And anything beyond 9.5 is not relevant, correct? So we're only interested in going from 0 to 9.5. So some of you can already eyeball what's going on here. I'm only interested from 0 to 9.5. I could do the same thing with 0. What happens if I cut out 0? The height of my paper is 0. What kind of box do I have? I don't have a box. I have a flat piece of paper. What kind of volume would that be? 0. That wouldn't hold any capacity either. So we know 0 doesn't work, and we know 9.5 doesn't work, but every number in between would make a box, correct? And we already figured out what it's going to be if we do 1 and 2. These are on your spreadsheet. And 3 and 4 and 5 and 6 and 7 and 8 and 9. So which one am I interested in? Go go ahead and cut out your corner and make your box. I'm interested in that point right there. How we figure it out? I'm going to use my extremum. I'm just going to click on it. What should my height be? 3.57. So with your scissors, see if you can eyeball 3.57 and cut that out of the corner. So just a little more than 3.5. And you can do that to all four corners. There, I cut out about 3.5. And you can make your box. You can take it home and you can put it on your refrigerator and you can say, did you know that this box is the largest possible volume that I could have made out of this piece of paper? And you can explain to all your friends and family how you did that. You can watch the class video of today and remind yourself of how it works. Okay, so how in the world would we have done this without GeoGebra? Would it have worked? How would you have known that it's 3.57? Is there any way you could have figured out this point without the benefit of your computer? Only if you know how to do calculus. So for those of you that are going to take like Calc 1, I know some of you are fish and wildlife majors, you will be able to figure that out in Calc 1. But as far as we're concerned, we can't figure it out unless we have a computer to do it for us, for what this class is doing. If you don't want to cut your paper box out, if you're done with this activity, that's fine. Before we leave today, let's make sure there's no paper on the floor so you can get it all into the recycle bin. When you're done with your scissors, I'll collect them from you.
Here's one more.
So what we did, when we punched in this f of x, we built the function. We built it using the height and the length and the width. And our answer is going to be in cubic units. So what we haven't even talked about the y value yet. If we cut out a box of 3.57 by 3.57 out of every corner, fold up the flaps, our box would hold 756.2 cubic centimeters. Cubic centimeters, right? And I think if you go back to the answers that you filled in, 4 gave us 748. But what did we just say we were going to get? 756. 756 is more than 748, right? So our best is 3.57, rounded to the 100th decimal place. Okay. I want to look now at the graph itself, the whole thing, from where it goes all the way down to right here and right here. And let's use a little bit of terminology that I gave you on that video. This is from section 5.2 and 5.3, which you can scroll through your textbook if you want. There's so much content in section 5.2 and 5.3, and I only want to touch on a few basics. We could spend a month on this section, okay? I only want to get a few of the basics. We've been making functions. We started out with linear functions, which were degree 1. Then we spent a lot of time on quadratic functions, which were degree 2. Those were parabolas that either opened up or parabolas that opened down. Okay? What degree is this guy on the board right now? 3. And if you didn't recognize that, it's hard to recognize because right now we have it in factored form. But if I multiplied this out and distributed and multiplied everything together, I have 1x there and 1x there and 1x there. It's going to be x cubed if I multiplied it all out and distributed, right? So it's a third degree polynomial. Okay? Notice how the tails go. Part of what we talked about, that I talked about in the video, is understanding what we call end behavior. The end behavior of a function. End behavior means what's going on when you go way to the left of the graph and way to the right of the graph, like out to a million, x equals a million, or x equals negative a million. What's going on with my tails as I zoom out here? As I move to the left, my graph goes down forever. You guys see that? And as I move to the right, my graph goes up forever. So that's what we're talking about when we say end behavior. What's happening at the ends? So this one we would say as x approaches infinity to the right, to the positive, we would say y also approaches infinity. Y is going up forever as x goes forever. What's happening when I go this way? As x approaches negative infinity, so as I travel way to the left on the graph, what's y doing? Y is approaching negative infinity as well. It's going down forever. That's what we call end behavior. And if you watch the video, you can see how you can identify that without even looking at the graph. You can look at this guy, and we already said if we multiply it all out, we're going to get x cubed, right? And if you have a x to the first power, like a line, you know that a line either goes this way or it goes this way. But you can't have both tails going the same direction on a line. Do you guys agree? One's got to go up and one's got to go down. What about a second degree? A parabola. Can you have your tails going in opposite directions on a parabola? No. They're either both going like this or they're both going like this. You can't go this way, right? So it's going to alternate now. What happens if it's x to the third? Are your tails going to go in the same direction or in opposite directions? Opposite. What about x to the fourth? Same. What about x to the fifth? Opposite. So the odd ones are opposite. The even ones are the same. Either there or there. How can you tell if it's going this way or this way on a quadratic? Negative or positive? Negative means it's going this way. Positive means it's going this way. So what about a cubic? How do I know if it's going this way or if it's going this way? Negative or positive? It's what we call the lead coefficient test. So if I multiplied this all out, here I have a positive x, here I have a negative x, and here I have a negative x. What's a positive times a negative times a negative? Positive. So this guy is going to be positive, meaning as it's positive, it's positive. And as it's negative, it's negative. If I would have inserted a negative sign in here, now I'd have a negative and the tails would switch, right? So I'm going over what I went over in that video. So you'll have to watch that if you haven't done that yet. So you should be able to identify the end behavior of a graph. How do you identify it? You ask yourself, what degree is it? Second degree, third degree, fourth degree, fifth degree. What degree is it? And then is it positive or negative? Its lead coefficient, and that'll tell you about it. How many times does my graph turn? Meaning changes from an increase to a decrease or changes from a decrease to an increase. I see 2 turns. This is one of my turns. Here I was increasing. I'm on the way up. Increasing, increasing, increasing. And then right here I turn around and I go down. There's turn number 1. And now I'm going down And right here I hit this and now I'm on my way back up. There's turn number 2. I talk about the number of turns in the video too, how you can identify the number of turns. And where does this guy cross the x-axis? Where are his roots? Where are his zeros? So in other words, where would the volume equal 0? We already talked about it. One of them is right here. If I don't cut any height out, it's going to equal 0. If I cut 9.5 out, remember I'd just fold it and it wouldn't have any width left over. So that would be 0. There's 9.5. And then the third 0 is actually outside the range of our activity here. But if you turn your brain off from the paper cutting activity, the next 0 is at 12.5. How many zeros does a third degree polynomial have? 3. Fourth degree is going to have 4. Fifth degree is going to have 5. We've talked about this when we were solving. However, not all of them are going to be real, right? So, for example, I could give you a graph that looked like this. That could be a third degree polynomial. It looks similar to what I have there. How many zeros does it have? Well, it has 3, except one of them is real, and the other 2, if you were to solve it, you'd get what in your answer? I, imaginary, complex, right? So, being able to build and identify features of polynomial functions, that's what we're doing. Okay, what I'd like you to do is go to the Desmos. I'm going to tell you right now that this Desmos is probably one of the tougher ones that I've given you guys to work on. It's 5.3, Constructing Polynomials. Everybody see it? Underneath course docs and links. I highly doubt you're going to get this done in class today. But I'm going to let you get started, and we'll talk a little bit about it in the next 10 minutes, and then your assignment will be to finish it for Wednesday. And it's going to reference a lot of the things that were in that video that I gave you. Notice the notation on number 1 is the same notation that I used up here describing this. So how you read that. As x approaches negative infinity. Another way to say that is as x goes way to the left of my graph, y goes way down. That's what negative infinity means, down. Positive infinity would be all the way to the right and up. Negative infinity all the way to the left or down, depending on if you're talking about x or y. Now, lots of yours are going to look different here. There's way more than one answer for these. I'm just taking some snapshots of some of yours here. Okay, I'm going to have you look at 4 of them here. What were the rules? What's my end behavior supposed to be doing? Both going. They're supposed to both go down, aren't they? If I read that correctly, it says as x goes to negative infinity, it goes down. And as x goes to positive infinity, it goes down. Aren't both y's going down? So right away, I see 2 of these guys that don't work. This guy's no good, right? And this guy's no good. This guy has both tails going down. This guy has both tails going down. So far we're good with those 2 with the tails, right? Their end behavior is appropriate. What was the other piece of criteria? It was supposed to have a root at 4. A root means a 0. That's where it crosses the x-axis or touches the x-axis. Does this person look like they have a root at 4? I think so, because I think each tick mark was worth 2, wasn't it? Did it say anything else about having other roots? Not necessarily. So I'd say this person's good to go. They have their end behavior good. They have their root good. How about this person? What? We already said this one was no good. How about this person? Do they have a root at 4? Yeah, they do. It's actually one that, and I talk about this in the video, sometimes when you have a root, it hits the x-axis and it bounces off. It just touches it in one spot. And other times it crosses all the way through. This person did a cross all the way through. This person did what we call a double root or multiplicity 2, where it's actually bouncing off. So I'd say both of those are correct. So there's a lot to think about here as you read the rules and try to construct it. But, 3 people might sketch a graph and be 3 completely different graphs, and all 3 of them could match the criteria that we're looking for. So there's not one correct answer to most of these. So step 2 is the exact same criteria, except instead of sketching it freehand, they want you to actually click on the things that you would multiply to make it happen. And again, there's more than one answer here. But as you click on all your things, look at your criteria 1, 2, and 3 and see if you're still obeying everything that it's telling you to obey. If you just look at some of them that are up on the screen right here, this person's end behavior, not correct, right? End behavior, not correct. What should both of our tails be doing? They should both be going down. Very quickly, 3 of these look good and 1 I don't like. Which one don't I like? Which one? Top left? Top right. The top right has the end behavior correct, but what's it missing? It's supposed to be going through the x-axis at 4. This person's good. 0 at 4. 0 at 4, 0 at 4. This person needs to be crossing the x-axis right here. Their 0 doesn't work, right? So 3 of them are good, 1 of them's not. Okay, I won't pause you anymore. You have a couple minutes to keep working. Like I said, this one might take you a little bit longer. if you're reading this and you're like, what in the world is going on? I don't know what I'm doing. That's why I gave you that video to watch on Friday and that video quiz that you were supposed to have done for today. So if you didn't do that, you best do that. So we'll pick up with this when we come back on Wednesday. Make sure you get all your paper into the recycle bin unless you want to take your box home with you. And if you have a scissors, you can put it in this box on your way out. And we'll see you on Wednesday.